Assalamu alaikum everyone. I'm Basil and I'm back, and in this topic we're going to be talking about min-max algorithm, and especially min-max with alpha beta pruning. It's got a very you can say crucial place in AI decision making, and it's a pretty good technique, and it's mostly used in like two player games where there are two players, one plays against it, or there can be a player and the computer, and both are trying to outsmart or out defeat the other one and to get the win. The best examples out there, or the most common ones, are like chess and tic tac toe, and you can apply it into other games as well. In easy and simple terms, what min max we can say is like it's a decision making for game theory, and what it does is like my minimum output or my minimum gain should be maximized rather than my gain opponent's maximum gain, and trying to outsmart it with decisions and traversals so that my opponent gets minimum and I get maximum uh, on different level of nodes. I'll show you guys an example forward in the video as well, where I have made a graph or a tree on my register showing how it works. So basically max node represents our turns, and minimum nodes can represent the opponent's turn, or vice versa. If it's the case of two players, player 1 and player 2, player 1 can be max node and player 2 can be min node, and if it's a computer then that. So let's just imagine playing a game where we can like score either 10, 0, or minus 10. Like positive 10, either we gain 10 points or we lose 10 points, or it's just 0. So we can play like that. The more moves we have, the more accepted moves we have, we're gonna get plus 10. Whereas if we lose a move, we're gonna get minus 10, and at the end, which is gonna have the most points is gonna win. That's simple. Now there comes a new terminology, which is alpha beta pruning. You can say it's a method or it's an algorithm in which we are going to prune or cut or ignore a certain branch of a tree, or a certain branch of, you can say, the game. For example, if I take door A, there are three doors in front of me, A, B and C. If I take door A, the computer is just gonna ignore door number B and C. It's gonna cut it off. It's not even gonna explore it because I chose A, and now it's gonna go and check all the conditions in A. If the A satisfies, if I choose B, it's gonna ignore A and C. It's not even gonna go down that way to look that if I could find something useful. Even if there is something useful, we are not gonna use it because we got something useful before it, and or it didn't satisfy, the parent node didn't satisfy, so we didn't went down till the child and subchild nodes just to check it, and that helps us in time and space as well. And what is alpha and what is beta? So these two are values. Yes, their signs are same, alpha and beta, the universal signs we use in every subject. But what is alpha? Alpha you can say like it's the best or the highest value, because we're here at highest and lowest, max or min. So you can say the best highest value that the maximizing player is gonna get or has or is guaranteed. It can have it, it's going to get it, or it's going to get it in future in certain branch. And what beta can be is it's the best lowest value that player can get. So like let me explain how it works. Is like, for example, we're standing at a parent node, and the value we got from our previous traversals or prunings is value number 6, or that node weight is 6. Now we're gonna go down, we're gonna look at the child of that parent, and let's just say that the best value we're getting from that child of that parent is 3. So what we're gonna do is we're gonna prune that branch. We're not going down there, we're not going to like risk going down there, because what we're gonna get is the best value we're gonna get is, if we go down there, is 3. And in that turn, I use that turn for getting the best value 3 rather than the best value 6 that I have. Then my opponent would get that value number 6 in his turn, and I will lose. So I cannot, like, risk going down the branch or sub child or child or any path or any decision which is gonna make me lose, plus it's gonna waste my time, because I already know I'm on a node where I have a maximum value or a better value than the child where I'm gonna go. So we're gonna prune it, we're gonna cut it, we're gonna ignore it, and we're gonna traverse up the tree and other branches to get the best and the highest value. And what it does, it helps me with time, it helps me with space, it helps me make decision faster and better. So here's the example that I've told you guys, and what I was telling you about. We're gonna look into it. I wrote some rules. I've already made it. I'm not making it live in front of you. It's already completed. But we start from the bottom. We got the bottom values, like at the real end of the tree, not the root. That we have here are like 3, 4, 2, 1, 7, 8, and so on. Plus the topmost node is max, and below that level is min, then max, then min. And at the max one, we are going to take the value of alpha, and at the min one, we're going to take the value of beta, the best possible value of beta at min. And then again on max, alpha. So in the first one, as you guys can see on the top, the alpha is not in you can say box which I made in black color. Beta is in a box, which means beta is locked and only alpha's value can be changed. Other than that, I've wrote it down on the top right. You can see its alpha is maximum and it's negative infinity, because we don't know at the start, we don't know the value, so we're assuming it's any number in negative infinity. It can be any number, because sometimes we get big datas and datas are in high number. We can't limit it to minus 10,000 million or 10,000 or 10 hundreds. It's not like that. Same goes for beta. It's in positive infinity. We might be getting data which would be like in billions. So if we put a limit of 10 million, then 1 billion data would not come here and we wouldn't get our sufficient answer. The condition for pruning we got here is alpha should be greater than or equal to beta. And if that's the case, we're going to prune. And it's the same way that I told you guys before. We're on a node, we got a better value, higher value, so we're going to prune it. Why go down there and get value number 3? So let's look at the example here. Starting The first, we start from the bottom, just like breakfast, bottom left. So we got number 3 here, and here we are on the min level. So here the value of beta would be changed. And when it's the value of beta, we're going to get the minimum value. We're going to accept the minimum value. The minimum value is 3. So we accepted 3 and we wrote 3 in that circle. Keep in mind the circle and the squares that I made didn't had any values. The only values we were given were at the end of these nodes 3, 4, 2, 1, 7, 8, 9, 10 and so on. Same way we go up, and now we're at the max level. We're bringing the value number 3 up to the max level. So at that time, alpha's value updates to 3. Now we go down, and what happens here is, look, we have a best value number 3. We went down the child's node and we found out that the child node had the best value number 2. So we're going to ignore it. Why? Because we're coming down with the locked value of alpha, which is 3. And at the min level, we're getting the value number 2. So alpha is greater than beta? Yes, it is. 3 is greater than 2. So we're going to prune it, and we crossed it with double lines, and we didn't went down the path to check what was at the end. It's gonna be 1. We already knew it. We're gonna traverse up. Same way, we're bringing the value of alpha here 3, but next node is the circle one, which is going to be the minimum, and it's going to get the value from the bottom node, which was 3. The best value which we got was 3. So the beta's value is going to be updated to 3, and alpha's value is going to be locked to minus infinity. We traverse down. Same way we look, and the condition we keep in mind is alpha greater than or equal to beta. Even if beta is equal to alpha, we're not going to go down that path. We're going to prune it. Same way I completed this, and the best value is at the top. So this is it. If you guys want me to do this example live for you, just let me know. I'll make another video, no problem. It's easy, and I'll explain it there as well. Now let's just conclude this topic, and alpha beta pruning, why we use it, it's mostly the most efficient ones we can use, because we put in a condition where it's not wasting our time, it's not wasting our resources, and we're getting the best answer, and we know it's confirmed that we're gonna get the best answer. Plus it's real world use. Its real world use is pretty much it's gonna apply to it. Any 2-player game, it's gonna apply to it, and it's gonna work best. Like chess, tic-tac-toe, and other games like carom, or you can say that I lost the word. It's like a football game we play on a table like that, billiards or whatever. So yes, hopefully you liked it, and I'll see you guys in the next one.